Have you ever seriously wondered what would happen if you fell into a black hole? I mean, really thought about it? These things are, without a doubt, some of the most extreme and fascinating objects in the entire universe. So join me. We're going to take a journey right to the edge of reality itself. And I promise, we'll make sense of some of the most mind-bending ideas in all of physics. So here's our game plan, our cosmic itinerary, if you will. First, we'll nail down what a black hole even is. Then we're going to explore its bizarre anatomy at what's called the point of no return. After that, we're taking the ultimate cosmic plunge to see what it's really like inside. Then we'll get into the deep stuff, the mystery where our understanding of physics just breaks. And finally, we'll see why these cosmic giants are so incredibly important. All right, let's kick this journey off with the main event, the ultimate mystery object itself. What is a black hole, really? So yeah, what exactly is this thing we're traveling towards? Because, it's not just an empty hole in space. No. It's something way, way stranger than that. To really get a handle on a black hole, you just need to understand three core things about it. First, imagine taking something massive, like a giant star, and crushing it down into a space smaller than an atom. The density is just off the charts. Second, all that density creates a gravitational field so ridiculously powerful that literally nothing can escape its pull. And third, well, because not even light can get away, black holes are totally, completely invisible. So where do these cosmic monsters even come from? Well, the most common kind are born from the death of a truly massive star. When a star like that runs out of fuel, gravity finally wins the war it's been fighting for millions of years. The core collapses in on itself with just unimaginable force and leaves behind a warp, a tear in the very fabric of space-time itself. Okay, so now we know what a black hole is. Let's get a little closer and check out its anatomy. Before we take that final plunge, we need to navigate the super treacherous territory around it, the point of no return. And this isn't just one single line, it's a series of regions, and each one is weirder than the last. Okay, this is the big one, the event horizon. Now, this isn't some physical wall you'd bump into. It's an invisible border drawn in space-time. Just think of it like the universe's ultimate one-way door. The laws of physics themselves guarantee that once you cross this line, there is absolutely, positively no turning back. And just outside that point of no return, there's another bizarre place called the photon sphere. Here, gravity is balanced so perfectly that particles of light, photons, get trapped. They don't fall in, but they can't escape either. They're just stuck, forced to orbit the black hole forever. Imagine this. You could theoretically see the back of your own head as light from it circles the black hole and comes right back to your eyes. Wild. And at the very, very heart of the black hole lies our final destination, the singularity. This is where not just our minds, but our actual physics completely break down. We're talking about a theoretical point where all the matter of that collapsed star is crushed into an infinitely small, infinitely dense speck. Space and time as we know them, they don't just bend here, they completely cease to exist. Okay, we've mapped out the neighborhood. Now for the main event. Let's really do this. Let's strap in and imagine what you would actually go through on this one-way trip. So as you get closer, something really strange starts to happen to time itself. If a friend was watching you from a safe distance, they'd see your clock ticking slower and slower. Then you'd cross the event horizon. For you, nothing. No bump, no barrier. It would feel like just another moment in space. But you just passed the point of no return. And now on the inside, the incredible gravity starts to pull on you directly through something called tidal forces. This is where Einstein's relativity gets really, really weird. For you, the person falling in, crossing the event horizon is a total non-event. But for your friend watching from their spaceship, it's a completely different movie. They would see you slow down, seemingly freeze right there on the edge of the black hole. And as the light from you gets stretched out, you'd look redder and dimmer until you just fade away. Your friend would never actually see you cross. Two totally different realities for the exact same event. Mind-blowing, right? And here we go. My favorite and probably the most terrifying term in physics, spaghettification. It sounds kind of silly, but it is deadly serious. The pull of gravity on your feet would be so much stronger than the pull on your head that the difference would stretch you out just like a piece of spaghetti. It is the ultimate and final cosmic stretch. So, in our little thought experiment, we've crossed the boundary and somehow we've survived. We're now in completely unknown territory. This is the place where our two greatest theories of the universe, Einstein's general relativity, the theory of the really big stuff, and quantum mechanics, the theory of the really small stuff, basically go to war with each other. And this conflict leads to one of the biggest puzzles in all of modern physics, the information paradox. See, quantum mechanics has a fundamental rule. Information can never, ever be truly destroyed. But if you throw something into a black hole, it sure seems like it vanishes forever. So where does the information go? Is there a typo in the universe's ultimate rulebook? Scientists are really wrestling with this one, and their ideas sound like they're straight out of science fiction. One theory, called the holographic principle, suggests the information isn't lost at all, but instead it's sort of smeared and encoded on the two-dimensional surface of the event horizon, like a cosmic hologram. Another idea is that it slowly, and I mean very slowly, leaks back out into the universe in the form of radiation. And that second idea is connected to this absolutely game-changing concept from the brilliant Stephen Hawking. Back in 1974, he figured out that because of weird quantum effects happening right at the event horizon, black holes aren't perfectly black. They should actually glow, just a tiny, tiny bit, emitting a faint heat. And this Hawking radiation means that black holes can lose mass and, over an almost unimaginable amount of time, completely evaporate into nothing. So after all of this mind-bending theory, you might be asking, why does any of this matter, right? Why do we spend so much time and effort studying these cosmic monsters? Well, let's take a look at how we've gone from just pure math on a chalkboard to actually seeing these things. Just look at this timeline. It shows the incredible acceleration of discovery. For decades, black holes were just this crazy prediction from Einstein's equations. Then things started happening fast. In '74, Hawking says they can evaporate. Then, in 2015, we didn't see a black hole. We heard one. We detected the gravitational waves, ripples in space-time from two of them crashing into each other. And then, the big one. In 2019, we captured the first ever direct image of a black hole's shadow. We went from pure theory to a photograph in a single human lifetime. That's just amazing. And that brings us right back to why they matter so much. Black holes are the ultimate laboratory. They are the only places in the universe where we can push the laws of gravity to their absolute breaking point. Studying them is our best shot at unlocking the deepest secrets of space and time and, maybe, just maybe, finding that holy grail of physics, a single theory that finally unites the tiny quantum world with the massive world of gravity. This quote really just says it all perfectly. Black holes aren't just cosmic vacuum cleaners. They are the crucibles where our understanding of the entire universe is tested and forged. They hold the clues to the next great leap in human knowledge, pushing us to ask the biggest questions. What other secrets are waiting for us out there, just beyond that point of no return?